Yay, I think we're working now. Okay. Technology is great when it works, and it's something else when it doesn't work. All right, so 3.1, the one we did with the video, where we're talking about ways to describe the middle of a data set. In this section, we want another description of our data that we're going to call a measure of dispersion. And that might sound really fancy. All it is how spread out is our data. So the idea here is we can have two data sets that have a middle at about the same place, but they can still look very different. Okay? So we could have, like if you're thinking about a curve or a histogram, we could have a bunch of our data, they're really close to the mean, or we could have our data really spread out, so maybe some of it's really far away from the mean. Okay. That's what we want to be able to measure and describe in this section. Okay, how spread out is our data? All right, so again, we're going to have three measures we look at, but this time, two of them we're really not going to use that much. And the other one we will depend on most of the time in this class. Okay. They are the range, variance, and standard deviation. And so let's look at the range first. The range is really easy. Find the range of a data set. We just take our largest data value and subtract the smallest one. So it really is what the name sounds like. It's just like, what range of values does our data cover? The big one minus the small one. Max minus min. It's really easy on this one. All right, let's do one. Okay, we don't have a lot to talk about there. We're just subtracting. So let's look at a couple of data sets here. We're told the following data were collected from samples of call lengths in minutes observed for two different mobile phone users. We want to calculate the range of each data set. Okay, so first we have to find the largest data value. So in A, what's the largest data value you see in there? Yep, 44. And then we're going to subtract the smallest one. What's the smallest one? 2. So we get a range of 42 minutes. Okay. Easy. All right. B, we want to calculate the range. What's our largest data value there? 44, and then smallest one's 2, so we get 42. Okay. So the point of this one, okay, range is really easy to calculate, okay, but if you look at those two data sets, if we're coming up with a measure of dispersion, you would think if two data sets have the same measure, the same number for how spread out they are, that they would look really similar when you look at the data values. But if we look at these two data sets, they don't really look like they're spread out in the same way. This one, we've kind of got data values kind of just all along the way, right? It looks like it's more evenly spread out. On this one, all the call lengths were 2 minutes except for one that was 44 minutes. You remember what we would call that 44-minute call? What type of value? An outlier. Okay. So it's going to be a recurring theme here. Outliers cause us trouble sometimes. And the problem here, okay, is this outlier causes the two data sets to have the same range, even though they're not really spread out the same way. Okay. If we take that 44 out, okay, so we're not including the 44, we just got a bunch of 2's, then what would our range be? It'd be 0, because our big one would be 2, our small one would be 2. 2 minus 2, we would get a range of 0. And that's really more representative of how this data is spread out, because they're almost all the same value. Okay. And so here a bigger number would mean our data is more spread out. So The range is really easy to calculate, but if we're going to have to deal with outliers, it's just not very useful. And so we won't use the range much. There is a different type of range we'll see later today. It's a similar idea, but you'll see when we get there. Okay, but we don't have to deal with the outliers with it, and it's more useful. But as far as just the regular vanilla version of range, it's not going to help us a whole lot. It is a measure of dispersion. So instead, we'll look at this next measure of dispersion, and that's called the standard deviation. So here we have our definition. It says it's a measure of how much we might expect a typical member of the data set to differ from the mean. And another way of saying that, how far do we expect a normal or just a general data value to be away from the mean? That's standard deviation. So we're going to look at the formula in a second, but so the idea here, we want to get the idea of what it's telling us. If we have a large standard deviation, that would mean we would expect our data to be pretty far away from the mean. So our data would be really spread out. Or if we have a really small standard deviation, we would expect our data values to be really close to the mean. And so we would have a more compact data set. Okay. So large standard deviation is more spread out. Smaller standard deviation, it's closer to the mean. Okay, so let's look at the formula here. Don't panic. Okay, not that bad. Don't panic. Look at the formula here. So what do we got going on? If it looks like Greek to you, that's okay, because a lot of this is Greek. Okay. No laughs on that. All right, no problem. Okay, so we got, that's a corny math joke, sorry. Okay, so we have this capital sigma here that's kind of glaring at us. All that means is sum. We're going to add some numbers together, so nothing to freak out over. Okay. We've got this Greek letter mu. If you watch the video, what's mu? Remember? It's like the Greek letter M, so it's the mean, right? It's the mean of our data. And then capital N is just how many population values we have. This is the population version of the formula. Okay. And then our symbol, okay, for population standard deviation is this other Greek letter. I know I told you this is sigma. That's the uppercase sigma. This is a lowercase sigma. Okay. So it's like the Greek S for standard deviation. It just looks to me, I always think about it like an O wearing a hat. So, all right, what's all this tell us to do? This says these x sub i's are just our data values. So it says we're going to take each data value and subtract the mean, the average from it. So we're saying how far away is each data value from the mean. We don't want those to be negative values, so we're going to square it. We do that for all the data and add it up. And then we divide by how many data values we had, kind of like taking an average. And then since we squared everything, we have to undo that by taking the square root. Okay, it's not bad. And even better news, I'm not going to make you, we're going to do one together with the formula. But beyond that, you never have to use this formula again. Okay? If you have a calculator that has statistical functions, it will do this for you without having to use the formula. Okay? The way that works on most calculators is when you go to the stats stuff on there, it'll pop up a little table. You fill in the data, tell it you want standard deviation, and it gives you the answer. Okay? But just so we can see what's going on with the formula, we are going to do one by hand. Okay? And after that, you can use a calculator. Okay? There's that. That's the population version of the formula. So population standard deviation represented by lowercase sigma. Remember, we usually use Greek letters to represent population values. If we are instead dealing with data from a sample, and we want the standard deviation of that sample data, then we have just a little bit of change. Okay, one thing that changes is that we're switching to our sample labels instead of our population labels. So here, instead of mu for the population mean, we use x bar for the sample mean. And instead of uppercase N for population size, we use lowercase n for sample size. And then if we're dealing with sample values for sample standard deviation, this one's easier to remember. Okay, we have S for standard deviation. Okay. And then we do have one mathematical difference. Okay. You may notice the thing that's actually going to change our answer a little bit. Yeah, the denominator. On the other one, for population, we just divide by n. We just divide by how many we have. But with sample standard deviation, we have to divide by n minus 1. Okay. Go down by 1. Yes.
Is there a difference in uppercase and lowercase?
The only difference is like where our data came from, where our numbers came from. So uppercase N, we're saying that's how many values we have in the population. Lowercase n, we're saying that's how many we had in the sample. That's the only difference. Only difference. Okay. All right. So why are our denominators different? That's a little tricky to answer at this point. So let me give you the short version. Okay. Remember, a lot of times when haven't got there yet, when we're doing like inferential statistics, we're trying to figure out something about a population by looking at a sample. So as we go forward, we're going to take these sample numbers and try to use them as an estimate for population numbers. And it turns out with standard deviation, it's not this way for all the different things we're going to look at, but with standard deviation, if we just use n, our estimate's always wrong. And it's not that it's always wrong necessarily, it's that it's always too small. Okay? No, too big, sorry. So minus 1, I'll make this one bigger. Yeah, so it's always too small. Okay, so we have to adjust, and the way we adjust is we do the minus 1. Okay? It just makes our estimate more accurate. That is a short version way of saying that. Okay. All right. Yes. Here? No, it's just a bar over the top. And all that is our way of specifying this, the mean. It's the sample mean. So this is an average. And then the reason is special, and then these regular x's are just data values. So I know that's confusing, but I didn't pick it. Okay, that's what we have there. To me, this one's a lot less confusing because they don't look the same. You can tell that's something else. It's not the same as this. That's what that bar is supposed to do for us. Okay. All right. So let's do our one by hand. Okay. See how the formula works. And really, it's mostly so you can be thankful you don't have to do the formula again. So, and let's take a look at one here. It says calculate the sample standard deviation of the following data collected regarding the number of hours students studied for a physics exam. Okay, and we have a small data set here. That is key because as your data set grows, calculating standard deviation by hand gets much, much longer. Okay, so doing these by hand is only real practical when you have a pretty small data set. Okay? So what we're going with here. All right, so if we look at the formula, and it says on this one, we're doing the sample version. It tells us these are sample values. So our formula, this last one, the one with the n minus 1 on the bottom, So if you notice something, we have a calculation we have to do before we can start calculating the standard deviation. Because we need to figure out X bar, we need to figure out the mean, the sample mean here. So that was from the video, right? To figure out the mean, that's what you normally call the average. Okay. We need to add up all our data values and then divide by how many we have. We have 5 here. Okay. So, yep, I think you're right. So we got to do that ahead of time. So, yeah, I think you get 35 over 5, so that gives us 7. And that 35 is just 5 plus 8 plus gives us 35. Okay. And we do have one other little ticky thing. You may remember from the video. With a mean, we want it to have one more decimal place than our data had. Our data here had no places after the decimal. So with our mean, technically, we want to write it 7.0. Okay. Now that's weird. The technicality, and kind of like you may remember, you may not. It's okay, but it's kind of like significant figures in science class. Anybody that ring a bell on somebody? Okay, so there's our mean. Now we got several steps to go through here. One thing that can be helpful, if you're trying to use the formula on these, is to make a little table. So here, the first thing we want to do with our data values is we want to take each data value and subtract the mean from it. So subtract 7 from it. Okay. That's going to be the first thing we do here. So I'm going to make a little table where we've got our data values. And so what were they? 5, 8, 7, 6, 9. Okay, and then we'll make a column where we're going to subtract the mean. Okay. Let me draw lines in here where it's easier to keep up with. Okay. So our mean, we said, was 7, or 7.0. Okay. So if we do 5 minus 7, we'll get -2. Then we'll do 8 minus 7. We'll get 1. 7 minus 7 gives us 0. 6 minus 7 gives us -1. 9 minus 7 gives us 2. Okay. And if we go back and look at the formula, the next thing it says we need to do, we need to take those new numbers we just got and square each one. So we'll have x minus x bar squared. So I have -2 squared gives me +4. 1 squared is 1. 0 squared is 0. -1 squared is +1. 2 squared is 4. And then I really made all my lines too long here. So there's the part where the little table is helpful. Okay. The next thing in the formula it says we want this sigma of x minus x bar squared. All that is we're going to take these numbers, right, that's this column, and add them all up. That's all the sigma says. We add all these up. So, yep, 4 plus 1 plus 0 plus 1 plus 4. 5 plus 5, so we end up with 10. And now we can actually plug in to the formula. And so we're trying, let me get a different color here just so it don't all run together. So here we're trying to find sample standard deviation. So the top part of this is what we just figured out, this sigma of x minus x bar squared, that's 10. The bottom, if you look at the formula, is n minus 1. That's our sample size minus 1. We had 5 data values. So that would be 5 minus 1 for 4 on the bottom. Okay. And then that part we can just punch in the calculator, it's okay. You don't have to worry about trying to simplify a fraction under a radical or anything, because we're happy with the decimal answer here. So square root of 10 divided by 4. So I get 1.58113, and it goes on and on. So that kind of lends itself to talking about how we round here. Okay. And our rule is the same as with the mean. Okay. We're going to round to one more decimal place than our data values had. So here our data were whole numbers. So we're going to round to one decimal place on standard deviation. So when we round here 1.58, that rounds up to 1.6. Okay. That's our standard deviation on this one. Okay. Questions on the pieces? If you do it one little piece at a time and use the little table, it's doable. But think about if we had 50 data values. Then how many rows would our table have to have? 50. Now you'd have 50 rows and then do 50 subtractions and then 50 squarings and then add up 50 numbers and then take the square root of that divided by sample size minus 1 and all that. Hey, it's a hassle. I mean, it's really, 50 is not even a big data set. Okay? What if we wanted to know like the standard deviation of the age of students at JSU? Then we would have like 9,500 data values. Okay? And that's not real practical. So, but back when they were starting to do statistics, man, it's like 1800s. Okay? So if you had a big data set, guess what? You got to spend all your evening calculating the standard deviation for whatever you're trying to look at. Okay? So it is the way they used to do it, but luckily we don't have to do it that way anymore. Okay? Technology has helped tremendously with that. Okay. All right, so before we leave it, what does this number even give us? Because if we just calculate it and we don't know what it gives us, that's not helpful. Yeah, standard deviation, and what does that mean? That means that we expect the typical data value to be about 1.6 away from the mean. Okay, so 1.6 what? In this case, our units are just the same as our data values. Here our units were the number of hours students study for a physics exam. We said our mean was 7. So we're expecting most of our data to be from 8.6, right? That's one standard deviation above the mean, down to 5.4. Okay, so this one's just a little bit bigger than 8.6. This one's just a little bit smaller than 5.4. So they're all about that range from the mean. That's what that's telling us. And if you only have 5 data values, that's not that impressive. And you can kind of tell they're all pretty close to 7. looking at it. But when you have a big data set, that's when the calculation really helps. All right, questions? You glad you don't have to do the formula? All right, so how does that work? I have some videos on Canvas for some of the most common calculator types that I see. Show you how to do standard deviation on there. If there's not a video for your calculator model, as long as your calculator says it has statistical functions, it'll do it. Okay. So if you don't have a video, you can just type in your calculator model, whatever numbers and letters yours is, and then just go to Google, okay, and then just say that calculator model standard deviation. And a video will pop up. Okay, it's pretty much guaranteed, okay, that somebody has made a video for your calculator model. Okay? And if you have any trouble with it, let me know, and I'll help you with that. Okay? I'll be glad to help you get comfortable with doing standard deviation on your calculator. Okay? So I'm gonna say this one more time for the homework. Okay? But I always feel bad for somebody that doesn't hear it. You do not have to do the formula in the homework. Okay? Just use your calculator to calculate standard deviation for you. Okay? I feel bad. There's always somebody or two that misses that somehow, and then they take like 3 hours to do the homework when it should have been 30 minutes. So, don't do that to yourself. Okay, so enough of that. If you have a graphing calculator, the ebook, or I'll just let the slides in. I'll walk you through. That's what we did. Okay, I'll walk you through some of these different calculations. So it gives you the directions in the slides if you have a graphing calculator. If you don't have a graphic calculator, it's fine. You'll just have to use one of the videos I have or find a video on YouTube. Okay. But I left the slides in here just in case. Okay, but this is what you'll get, something like this, okay, on your calculator. The graphic calculators have a big screen, so they spit out this stuff all at once. Okay. It might be kind of hard to see, but on this one, that would be the number we wanted because we were calculating sample standard deviation, so it's S. If it said there were population values, we would have used the one that says sigma. If you have a calculator with a smaller screen, you probably have to scroll through. And it's a little different from calculator model to calculator model. So, but you should just have a little table. You put the data in, so those 5 data values, and then go to whatever menu, and it'll spit out the stat stuff. Much quicker than the formula. All right. So let's think about this situation. Says Mark's looking into investing a portion of his recent bonus into the stock market. While researching different companies, he discovers the following standard deviations of 1 year of daily stock closing prices. Okay. We've got the Perfacto Corporation, a standard deviation of $1.02. We've got the Artismith Company, has a standard deviation of $9.67. We want to think about what these numbers mean to us. So, one pitfall when you're first learning about standard deviation, this does not tell us what the actual price of the stock is. Okay? It could be $500 a share, or it could be 50 cents a share. Okay? This is telling us about the standard deviation of the prices. Okay? So what does that mean? This tells us how far away from the mean, from the average, we can expect the stock to go on a typical day. Okay? So this is telling us on a typical day, it would make sense for this company's stock to fluctuate by $1.02 around the mean. Okay? But for this one, it would make sense. We would expect that its price is going to fluctuate almost $10 around the mean, $9.67. So as far as variability, you could say. Or you could think about how much do the prices fluctuate. Okay. Here we've got a smaller standard deviation, so we could say we're expecting there to be less variability in the price of the stock on a given day. So it's fluctuating less, okay, or a smaller amount normally. And then this one's fluctuating more on a given day. You know? So if this one goes up by $10 or goes down by $10 someday, we expected that. If this one goes up by $1 or down by $1 a given day, we expect that. Okay? If this one goes up by $10 on a given day, that's unusual because its standard deviation is only $1.02. Can I get the idea of a little bit? Okay, let me, let's see. So if you're like tracking the graph of the prices, we don't know what the numbers are on the price, but so like this one, we expect to go up and down a little bit every day, right? About $1. This one, we expect it to go up and down and up and down and up and down. More, bigger jumps, okay? More variable. Okay? So they could both be headed in the same direction. Right? They could both be going up or they could both be going down long term. Okay? But short term, Perfecto's less variable, Yardsmith's more variable. Okay? You could say Yardsmith's more volatile almost. Okay? So we've got a couple questions to answer here somewhere. I'll get on the same page with you in a second. Okay. So if we're trying to get a nice, stable, steady investment, which one do you think would be the better choice based on the standard deviation? Which one you say? The first one. Okay. Because it's not going crazy every day. It's only changing by about $1 typically. Okay, so that would be our more stable thing. If you were hoping that you could dump a bunch of money in a stock and leave it in there just for a few days, hoping it's going to shoot up, and then sell it off and try to make some money real quick, which one would be your better choice? Be the bottom one. Okay? Because it fluctuates more day to day. Okay? So another way you can think about these is with money, standard deviation, we can think about it as risk. So one thing we could say is that Perfecto is less risky and Yardsmith is more risky. Okay? Because here, if you're dumping that money in, it could shoot up, okay, more in a day. It could also go down more in a day. Okay, so you have more risk there. You make that investment. Okay. Questions? And that is not enough information to go throw a bunch of money in the stock market. Okay, so that's just a piece of the picture. Okay, things you want to think about. So one more measure of dispersion, and it should look familiar. It's called variance. Should look familiar because all it is the standard deviation squared. Square a number. And really what's happening on the formula is it's exactly the same as the standard deviation formula, but without the square root. We're just not taking the square root. So variance is actually a little more intuitive in some sense, because if we look at our definition, it's kind of like we're thinking about like the average distance we can think about the data being from the mean. So here we say how far is each data value from the mean and divide by how many we have. We have to square it here because if we, just by thinking about the mean's right in the middle. So if we just added up all the distances, we would get 0. And because they would average out, we'd have, for every one that was above the mean, we would have one below the mean, and that would cancel each other out. That's when we square here. So a variance is a little more intuitive. Why do we focus more in this class on standard deviation? And the answer to that is because here, the units are also squared. Everything's squared here. And our symbol even helps you remember that, right? The symbol is just sigma squared instead of sigma for standard deviation. So sometimes that's okay. Like if our data is in inches, then our our variance would be in square inches, and we kind of have an idea what square inches mean. Right? Think about area, but it usually doesn't apply to the context you're working in, and it can be even weirder. Like, what if our data is dollars? We're dealing with money. Then what is a square dollar? I have no idea. It doesn't have meaning. So what good is it to say my variance is $1,200 squared? Okay. So that part is not all that meaningful. We don't have that issue with standard deviation because we take the square root. So if we're dealing with dollars, our standard deviation is in dollars. If we're dealing with inches, our standard deviation is in inches. So same units. So we tend to go with standard deviation in here. Okay. You will occasionally, as we go forward, and I don't have control over it, okay, occasionally some of the problems where you need standard deviation in Hawks will throw you a little bit of a curve and give you variance. All you have to do is remember, if it gives you variance, to get standard deviation, what do you have to do? We have sigma squared and we want sigma, take the square root, take the square root. And the same thing is true for the sample version. If it gives you sample variance and you want sample standard deviation, take the square root. Take the square root. Okay, so if we want S, that's just square root of S squared. So that's variance, and we're not going to calculate one because it's exactly like standard deviation, but without the square root. I did leave the little graphing calculator instructions in here. Next thing is this little table I made for you, because it can, getting the learning the symbols can be a little tricky to start with, can be a little confusing. So you might want to sketch this little table out to help you as you're working through these, and just to keep track of the symbols. If we're dealing with sample values, we're going to have S. If we're dealing with population values, we're going to have sigma. If it's standard deviation, it's just the regular symbol. And if it's variance, it's symbol squared. When that can be confusing is like you have a problem on Hawks that asks you for the population variance of some data set. Well, you can get your calculator to tell it to you, but it's going to give you S and sigma, and you have to decide which one you actually need. So if it said population variance, that means you need sigma. Okay? And not only do you need sigma, you want variance, so you would have to take that number and square it. So just keeping track of all that, this little table can help. Okay. Okay. Questions there? Okay. Anything? All right. One last little topic here in this section. We'll be moving on. Okay, and that is called the empirical rule, or the empirical rule for bell-shaped distributions. So this just falls here because now we have talked about standard deviation, so we can finally talk about the empirical rule. So what the empirical rule tells us, and it is important here that this only applies to bell-shaped distributions. So those distributions we have that look kind of like that, hill. So that might seem really limiting, but it turns out that a lot of different types of data you collect turns out to be this shape when you plot it out. That's really common. So the empirical rule tells us for those bell-shaped distributions where we can expect most of our data to be. So the mean on the bell-shaped distribution is going to be that line right down the middle. So we'll have some number for our mean. And then we've got 3 statements about where our data values are going to be located compared to the mean. Okay? So the first one says that if we go out 1 standard deviation from the mean, so that's saying we calculate our standard deviation, figure out what that number is, and if we take that number and go up from the mean that much, and then go down from the mean that much, so within 1 standard deviation above and below the mean, that we're going to have about 68% of our data in that range of values. And so more than 2/3, 68% of our data is going to be within 1 standard deviation of the mean. And then same idea on these others, but we're just going out 2 standard deviations. So add the standard deviation twice, subtract the standard deviation twice from the mean, and 95% of our data is going to be in that range. So 95% within 2 standard deviations. And then these are rounded, is why it says approximately. We can get exact numbers, but we're just rounding. And then if we go out 3 standard deviations, we got 99.7% of our data in that range. So that might not seem all that useful right now, but it is. This is really one of the most useful things we talk about in the class. We'll see some applications as we go through. One thing that does for us that we can talk about now is it kind of tells us a way of taking a data value from some data set and figuring out if that is what we would call like typical for that data set, or is it unusual for that data set. So how can we do that? Well, I mean, one thing we can think about that hopefully you're familiar with is IQ scores. Okay? So IQ scores would fall in a bell shape. Okay? Depending on which type of test you take, and they usually have the mean set up to come out at 100. So our middle value here would be 100. And usually the standard deviation, again, depends on the type of test, but is about 15. That means 115, let me get a different color. 115 would be 1 standard deviation above the mean. And then 130 would be 2 standard deviations above the mean. And then 145 would be 3 standard deviations above the mean. Okay. So it's probably kind of intuitive, but how unusual is it to see somebody that has an IQ greater than 145? Real unusual. Okay. That would be somewhere over here. And the empirical rule tells us most of our data is in here. Okay, so it's out there in a weird spot. and to have somebody with an IQ that high. How unusual is it? That's really, we can put numbers on it. Okay. So here, 99.7%, we've got 100% total, so that would mean there's 0.3% here and on the extreme over here. So just on this side, that would be 0.15%. Okay. There's only a 0.15% chance that somebody's going to have an IQ greater than 145. It's real unusual. Real unusual there. So kind of one way we can use the empirical rule. Okay. Or you can also say, what about a person that has an IQ of 105? Is that bad? No. It's here with everybody else. Okay. It's in here with more than 2/3 of everybody else. Okay. That's typical, normal. Okay. Even, what about 100's average, right? So what if somebody has an IQ of 95? Is that bad because it's below average? Not really, because it's in here with 2/3 of everybody else. Okay, this is saying 2/3 of people are going to have more than 2/3 going to have an IQ between 115 and 85. Okay, so that's one way we can use it. Okay. Anybody know your IQ? I'm not asking what it is. I'm just asking, does anybody know what yours is? Nobody in here? Okay. Usually most people don't. And don't trust Facebook. So we can use this empirical rule to solve some problems. And so let's look at a few problems, and let me show you how I work these, and then we'll be done with this section. So there's just a picture of what we were saying. If we go 1 standard deviation above and below the mean, we got 68%. We've got 2 standard deviations above and below the mean, 95% of our data is in there. And then if we go 3 standard deviations above and below the mean, almost everything, 99.7%. So if we have data value out here, it's really weird. Usually, depends on the context, but usually if you have something more than 3 standard deviations away from the mean, we would definitely call that an outlier. Okay. Sometimes do 95%. Okay. All right, let's look at this one. Okay. This one says the distribution of weights of newborn babies is bell-shaped with a mean of 3,000 grams and a standard deviation of 500 grams. Okay. So we need that information to set up our distribution, okay, and know where the numbers on the curve are. A says what percentage of newborn babies weigh between 2,000 and 4,000 grams? Okay. So we can use the empirical rule to answer this question. Okay. So the way I work these, no matter what it's asking me, is I start off drawing the little curve, the little bell-shaped curve, okay, and then I label it. Okay. So I'm gonna got a blank side here. So I'm gonna draw my little bell-shaped curve. Okay. And then here's my axis down here. Okay. And then I'm gonna label it. So it told me in the setup to the problem that the mean, what was it? The mean was 3,000 grams. So I know that's the number that's right here in the middle, 3,000, because it's symmetric. And then it said the standard deviation, what was it? It was 500 grams. So the standard deviation tells me how much to go up for each step. Okay, we're going in steps of standard deviation. So like if I want to go up 1 standard deviation from the mean, I do 3,000 plus 500. That's 1 standard deviation. So 3,000 plus 500, 3,500. And then we can go up another step. We add 500 again, get to 4,000. And then do the same thing one more time. So plus 500 more, get to 4,500. And then we can do the same thing going down below the mean. We do 3,000 minus 500. This is 2,500. and then minus 500 more gives us 2,000, and then minus 500 more gives us 1,500. And the reason why I'm only going 3, not 1,000, the reason why I'm only going 3 is because that's as far as the empirical rule tells us about, okay? So we just go out 3 standard deviations and we're good there. Okay, sorry, it's kind of low on screen. Okay. So I do that, and then I label it one other way. Okay. I'm going to, instead of having it in grams, which is the units we're dealing with our data here, I'm going to label it in terms of standard deviation. Okay. So I know the mean is here in the middle, so I'm going to call that 0, because the mean is 0 standard deviations away from itself. And then we added 1 standard deviation to get here, added 2 to get here, we added 3 standard deviations to get there. And then the same thing going down. We took away 1, took away 2, took away 3. Okay. And if you make that little sketch, you can answer any kind of empirical rule problem. Okay. So that's how I start off. And once you do some of them, like you'll quit drawing the curve and just have the number line and things like that. You'll get more comfortable with it. That's how I start out. Okay. So then now we can look back at our question. Okay. It says, what percentage of newborn babies weigh between 2,000 and 4,000 grams? So we're wanting to know what percentage of newborn babies weigh between here and here. What percentage of our data is in that range? Good, 95. You've already seen what we're doing. That's 2 standard deviations above the mean to 2 standard deviations below the mean. So the empirical rule says that in this range of values, we've got 95% of our data. Okay. Questions on that one? Hawks shows you a little bit different way to do it. So if you want to do learn in Hawks, you can see a different way if you don't like that. But I like having the thing to look at, picture. Okay. Look at B part then. B part is trickier. It says, what percentage of newborn babies weigh less than 3,500 grams? Okay. So this one's trickier because it's not asking us what percent we have between 2 numbers. That's what the empirical rule tells us is between 2 numbers. It's asking us what percentage are less than some value. So we have to be a little bit more creative. We can't just use the empirical rule. We have to use some other piece of information here. But let's look at the picture and see what it's asking. And so we want to know less than 3,500 grams. What percentage of our data is in there? So let me get some different color here. So we want to know what percentage of our data is from here, less. That goes all the way down to 0. Okay. In theory, it goes all the way down to negative infinity, but you don't have many babies that weigh negative weights, so we can think about it going to 0. Okay. So what's our missing piece of information? Okay. Well, we got to go back. We got to go back a chapter. Okay. What shape would we call this bell-shaped distribution out of our 4 shapes? Remember? Symmetric. It's symmetric. So, since it's symmetric, if we draw a line right down the middle, okay, so here's our line right down the middle at the mean. So, how much of our data, what percentage is going to be to the right of this line? 50%, good, because it's symmetric, right? Means we have 50% on this side, 50% on this side. So from here down, we've got 50%. But that's not all we want. We also want between here and here. So this piece is 50%, and then we got a little more we got to add on. So that's our last task, is to figure out how much we're adding on. So we're trying to figure out between 0 and 1 standard deviation, what percentage we would have there. Well, what percentage would we have between 1 and -1? 68, and is symmetric. So how much is going to be on one side of that? 34. We're divided by 2. Right? So we know between here and here we got 68%. We don't need that whole thing. We only need half of that. So that's 34%. Okay. So we've got 34% in this little piece, 50% from there down. So on B, we just add those together. So what percentage of newborn babies weigh less than 3,500 grams? 84%. So a little trickier. We had to use the symmetry there. Once you see the symmetry trick, it's not as hard next time, okay? Because you've seen it already. Kind of hard to think about the very first time you have to deal with it. That questions on that one? That one's a little confusing, maybe. All right. Okay, one more, and it's easier. It asks a question the other way around. It says, figure out the range of birth weights that would contain the middle 68% of newborn babies' weights. So 68% of our data is between +1 and -1 standard deviations. So then we would just have to look at our picture and see what those numbers are. So here, +1 would be 3,500 grams. That would be the max. And then -1 would be 2,500 grams. So that would be the minimum. So on C, our range of values would be between 2,500 and 3,500. Questions?
Less than 500.
You got it. Yeah, that's a good, very good. So yeah, like, good question. So if it said on B, the purple one here, if it said less than 2,500, we would know this much would be 50%, but we would have to subtract a little piece. And that little piece we would have to subtract would be between -1 and 0. So again, that would be half of 68%. So we would have to subtract 34% instead of adding it. Yeah. Good question, because you will have ones like that. So. And one other thing we'll mention here, I'll just help you on the homework, okay? Sometimes it'll ask, like, what percentage of newborn babies weigh more than 4,500 grams? Okay. So there, we know that between 4,500 and 1,500 grams, we've got 99.7% of our data. But that leaves a little piece over here on this side, and then a little piece over here on this side. This little piece on this side is what we want, okay? But we don't want all of it. So what can we do? We can do 100% minus the 99.7% that's in here. That'll tell us how much is on both sides, but we only want one side, so you divide by 2, and it'll give you the percentage up here. So 0.15%. Okay, that is 3.2. Done with that one. And if you have empirical rule trouble, if you're running into any of these that you're stuck on, bring them to class. Okay, bring them to class. We'll work them together. Okay, you can email me too if you do that. All right, so that section down. Let's see if we can get PowerPoint to work for our other section here. We'll get a little bit of it done. Doesn't look like we'll get finished with it. Okay, one day. There we go. 3.3. It's an easier section. Okay? You don't have to deal with standard deviation and stuff like that. Okay? This one, we're talking about relative position. So we talked about where the middle of our data is, how spread out our data is. And then in this section, what we're really wanting to do is we're wanting to talk about, like, if we have one data value, how can we describe where in our data set that data value falls? Or if we have two data values, how can we compare the two? How can we compare the two? So that's relative position. Okay. So we're going to talk about percentiles, quartiles, and something called the 5-number summary. Those all kind of go together. And then we might get through that. And then you can make a graph out of the 5-number summary, so we'll see that. And then there's one other thing called a standard score that's not listed here. That'll be next week, probably. All right. So the first thing to talk about here is percentile. And you don't have to write this formula down. We're not going to ever use it. Okay? I've got it here just so we can look at it and talk about it, but I'm not going to have to use it. So the main thing on this slide is for us to look at the definition. It says here to get the percentile, all we have to do is count and divide. Okay? So this, we'd have to put our data in order, and then if we wanted to know what percentile a certain data value falls at, we count what place it is out of how many data values we have and turn that into a percentage. That's all it is. So our definition says we're counting how many data values are less than or equal to the value we're looking at. So if we see something that's at a certain percentile, that means that that percent of the data is less than or equal to that value. Okay. And if you think about it as a picture, okay, if we say something like, that was a bad one. You say something like we have this data value here that's at the 35th percentile. Okay. Well, that means that 35% of our data falls less than or equal to that value we're talking about. Okay. What percentile means. So if you take a test, this is where you're probably most familiar with percentiles. If you take a standardized test and it says you scored at the 85th percentile, does that mean you did good or bad? It means you did good. That means that you scored as good or better. Or you could say that other people scored, 85% of other people scored the same or lower than you. Okay. Okay. And then 50th percentile is right in the middle, right? That's 50% on each side. So. Okay. Got the idea of percentiles? Just means what percent of the data is less than that, or the same percentile. Okay. So we're not super interested in that. Okay. We're more concerned with 3 special percentiles, and they're percentiles that divide our data into quarters, into 4 pieces. So since they're percentiles that divide our data into quarters, we call them quartiles. Okay, quartiles. So we're just putting the 2 words together. So the first quartile, Q1, you can shorten it to that, is the 25% mark. Okay? So that represents the first quarter of our data, first 25%. Second quartile is like the 50% mark, and the third quartile is the 75% mark. Okay? So we're just splitting our data into quarters. One of these we've already seen before, actually. We just called it something else. What you got? Well, which one have we seen before first? Can you make a guess? Second, yeah, because we talked about the middle. So it says 50% of our data is on one side, 50% of our data is on the other side. So what was our, remember what our name was? It was in the video. Not necessarily the mean, but it is always the median. The median. And so Q2 is just another name for the median, the middle number, right? If it's the middle number, half's on one side, half's on the other. Okay? So lots of times instead of saying Q1, Q2, Q3, you'll say Q1 median Q3. I mean the same thing. If our data is perfectly symmetrical, the mean and the median are the same number, and that's true. In general, that's not true. Okay? So there are our quartiles. So we want to talk about how to find these. So if we have a data set, how can we pick out the first, second, and third quartile? Okay. So it's pretty easy. Okay. We're gonna do two different ones, and then after we do those two examples, I think you'll be masters. Okay. Not hard. So let's look at this one. We've got these following are speeds of motorists that were obtained by a highway patrol officer on duty one weekend. We want to find the quartiles for each data set. And it says using the approximation method. That's the only way we're going to do it in this class. So if you see that on a problem, don't let it concern you. Okay, we're only going to do it one way. So, all right. So the first thing we need to do is make sure that our data is in order. Okay? And this one's already in order, luckily, because that's a pretty long set, had to put it in order, but this one's already in order, and I've got it on the next slide, so we'll have some room. So let's look at data set A here. Okay. Already in order. We want to find Q1, Q2, Q3. We said Q2 was another name for the median. So since we already know how to find the median, let's start with Q2. Okay. So there, what we want to do, since it's kind of a big data set, you probably want to mark numbers off on each end to get to the middle here. So let's see what we get. I'm gonna underline so I don't mark them out. Okay, so we have this situation where we have two middle numbers. So 70 and 71. So how do we find the median in that case? Do you remember? Add them, divide by 2. Okay, so there Q2 would be 70.5. Okay. All right, now we need Q1 and Q3. And we got a little trick that makes this easy. Okay. If we take and we split our data into an upper half and a lower half, so we're going to look at that piece and that piece separately. Okay. What that does for us is then Q1 is just going to be the median of the lower half of our data. Q3 is going to be the median of the upper half of our data. So we just have to find the median again. So on the lower half, what's Q1 going to be? 65. Yeah. And then on the upper half, 78. Yeah, that's not quite too big to be able to look at it and tell here. 3 on each side, so 78. That's Q3. And it's pretty easy to look at it and say, okay, if I'm here, 25% of my data is less than that, right? Less than or equal to. If I'm here, half of my data is less than or equal to that number. And that's what we're after. Okay, so there are 3 quartiles. Hey, let's look at B. It works just a little different. And we want to find the same things though. Q1, Q2, and Q3. So we'll start with Q2. So looking for the median. And we got one middle number on this one, 75. And it's important that you keep track of which, since 75 is on there more than once. Okay? You know, we have a particular value of 75, that gives us our median. And the reason why that's important is now when we split our data into an upper half and a lower half, we're going to leave that 75 out because we've already used it. We'll split it like this. Okay. So that's the only little trick you have to remember. If you have one middle number for Q2, don't include it when you split the data into the lower half and upper half. Then Q1, 67, and Q3, 79. Find the median of the lower half, median of the upper half. We're done there. Questions on those? They're not bad. Okay. One other thing to mention, and then we'll pick up the rest next time. Okay? So these are our quartiles. And if we add in two other numbers, we get what we call the 5-number summary. Okay, so imagine you have somebody that can't see the data, and you're kind of trying to describe what your data set looks like to that person. Okay? So the 3 quartiles would be good numbers to give them, because then they'll know the middle number and they'll know, the first quarter, the last quarter, kind of get an idea how spread out it is and things. Can you think of any other numbers in the data set that would be important? First and last, the minimum and the maximum is what we'll call them. That way, because you need to know where it starts and where it ends. So if we take those 5 numbers together, the minimum, Q1, the median or Q2, Q3, and the maximum, that's what we'll call the 5-number summary of the data set. Gives you lots of good information about what the data set looks like. So that's something you need to remember, is what numbers are in the 5-number summary. Minimum, the maximum, and the 3 quartiles. All right, next time we'll turn these 5-number summaries into a graph. We'll call a box plot. Okay. We'll pick up there on Tuesday. Okay. We don't have too much left on this one. If you did not get on the sign-up sheet, let's see, where'd that make it to today? I got that one back there in the back. Okay. Yeah, just if you will, when you get finished with it, just bring it up here to the front. We'll put it up here. Okay. Make sure you get on there before you leave, and I will see you next week. Okay. Have a good long weekend.
Have you posted this PowerPoint?
It may not be up there yet. I may have forgot. I think I'll have to double check.
Okay.
If they're not there, I'll get them there.
Okay, thank you.
You're welcome.